Okay, so we are in Statistical Rethinking, second edition, chapter 16, and we're going to knock out questions 16H3 and 16H4, as you know, basically 16H4 is a continuation of 16H3. Okay, so here's the question. Earlier in the chapter, we used an ordinary differential equation model to model the differing and changing populations between lynxes and hares. And so now we're going to model that data differently by a way that was suggested in the text, or not recommended, but something that we could do, and that is using an autoregressive time series. So in other words, the number of lynx and or hares at any time period is predicted by the number of lynx and or hares in the previous time period. Okay, and so we are regressing variables on themselves. Okay, so that's why it's a time series or an autoregressive time series. Okay, and so each time period that is one behind, the one that we're considering is called a lag variable. Okay, and so the question tells us how to create these lag variables, but basically if we're looking at observation t, well then the lag variable is t minus 1. Okay, and so this gives us the code how to do that right there. And then this is the model that will instantiate into rethinking or Stan or whatever. So it looks like this. Okay. And so notice that this would be lynxes at time t, and it's a log normal distribution with mean log mu, where mu is the thing that has the linear component of the model, and it has as components, it has an intercept, and it has the lag variable for the previous time period, the number of lynxes in the previous time period, and the number of hares in the previous time period. Okay, and then similarly for the number of hares as we go across time. Okay, all right, and then we're going to compare this to the ODE model. Okay, so the first thing I'm going to do is I'm just going to run the ODE model because we're going to need to compare it eventually. So we just run that and get that out of the way. This is really just copied and pasted from the book. Remember that this was done completely in Stan, and that code is just available in the rethinking package, and you can look at the code and so on and so forth. But we run that just so we have it, and we see that it converged. Looks okay. We should run some trace plots or something, but we'll just kind of keep moving here. And we have these different parameters that are not necessarily easy to interpret. That's why we want to plot these things, and we will here eventually. Okay. So now we're going to run the autoregressive model. Okay. So we have the data as constructed as we're instructed to do, and then we're going to build the model here. Okay. And so for lynxes, so this is my little model for lynxes. Okay. So this just follows the definition that we had up here. And then notice how we are building or using these lag variables. So each lag variable, so lynxes at the one period before is given here, and it gets its own beta coefficient, right? It's just like any other predictor. And then we assign some priors to the beta coefficients. Okay, and so for here, I'm assigning probably positive priors to the beta coefficients. Okay, so what is this saying? Okay, so let's first look at the beta LL, or lynxes. The number of lynxes in this time period as predicted by the number of lynxes in the previous time period. Okay, well, we might suspect that if there was a lot of lynxes previously, then there's probably a lot of lynxes right now, right? Because more lynxes make more lynxes, roughly speaking. Okay. Okay. Now, of course, there could be knock-on effects where lynxes start competing for territory and then some starve or something like that, and or they fight, or I don't really know what lynxes do, but we're ignoring those complications here in this model. Okay. Okay. Well, what about this other coefficient? It's the number of lynxes based on the number of hares in the previous time period. And once again, if there was a lot of hares in the last time period, well, then those are a food source for the lynxes, so that's only going to encourage there being more lynxes. Okay. And similarly, if there are few hares, well, then we might predict that that's going to have a knock-on effect at this time period, decreasing the number of lynxes. All right. Now we go into hares. Okay. And so now for the coefficients, I'm using gamma. I'm calling them gamma just as a way of distinguishing between lynx and hare coefficients. But and so for gamma HH, in other words, the number of hares in this time period as predicted by number of hares in the previous time period, well, we make a similar argument as for beta LL up here. There was a lot of hares last time, and there's probably a lot of hares this time. But now we have this negative, or probably negative coefficient, right, for the prior, for HL, the number of lynxes in the time period. So again, the number of hares in this time period based on the number of lynxes in the previous time period. And it makes sense that this should probably be negative, right? Because if there was a lot of lynx last year, well, those are going to eat a lot of the rabbits. So the more lynxes there are, there should be proportionally fewer hares. Okay, so that's kind of how these get determined. So we run that, and everything converges, and that's fine. Again, understanding the coefficients isn't exactly straightforward. So we're just going to plot these and compare them. So you can look at the code here, but this is what it looks like. And let me zoom in here. Okay, so the ODE model is right here. It looks however it looks, but the AR model, the autoregressive model, does seem to be missing quite a bit of the data, right? So at least in this case, the ODEs are probably doing better. Now we might complicate the AR model, in any number of ways, but at least with what we've done here, it's probably doing worse than the ODE. Okay. All right. So now moving on to 16H4, we're basically going to expand the AR model by adding a second lag, so 2 time periods back. Okay. So now we have not only one time, we not only have lag 1, but also lag 2. Okay. So we need to make our data set here. Okay. So I've done that right here. It's basically copy and paste the previous data set, but we add a lag 2 here. And then notice how, well, if you compare it to AR1, we have to kind of push the left boundary of everything over by 1 and push the right boundary, back by 1. So I'm not sure if that exactly makes sense, but if you compare it to AR1 here, you see the pattern that we need to use in order to to make sure that every observation that we put into the model has both lag 1 and a lag 2, right? Okay. So we have that. And now we're just going to modify the model that we had previously by adding this lag 2 term here. Okay. So it's the same model, but now we have these lag 2 terms. Okay, here. And so, again, we can go through and make the same arguments about the directionality of all of the priors. And so I'll let you do that, but there's one here that's maybe worth highlighting. So if you remember from the previous example, okay, we had that gamma HL, again, the number of hares in this time period as predicted by the number of lynxes in the previous time period, was probably negative. Okay, and we went through the explanation for that. And that is still true here, but now when we look at the second lag, it's probably positive. Okay, and so that could be a little bit misleading or a little bit confusing, but hopefully that makes sense, right? So if we're going through alternating time periods, where the lag 1 in each time period is negative, well then, the next time period should be positive. Okay, I'm not sure if I'm really explaining that well. Okay, but okay, if the number of hares in this time period based on the number of lynxes in the previous time period is negative, well now if we do another negative for time period 2, right, or lag 2, well then the negatives cancel out and now it becomes positive. Okay, so I hope that makes sense to you. Okay, so this is what we have. This is our model, and we run it, and it runs fine, converges and everything. And so once again, we will just plot everything. So I've just copied and pasted basically the same code from above and added the AR2 model, and we get this. And we'll zoom in. Okay, and so here's the AR2 model, and it really doesn't seem to be doing that much better than the AR1 model here. So again, we might continue to try to complicate these AR models, but at least with what we've done here, the ordinary differential equation model is doing the best. Okay, we'll call that good.